I want you to picture the most boring day of your life. You are sitting in a dusty lecture hall. The air conditioning is humming. You are staring at a blackboard covered in white dust. The professor draws a diagram. You know the one? A ceiling, a vertical line, and a box. If you have ever taken a physics class, you know this image. It is a running joke of the scientific world. Humanity has split the atom. We have detected gravitational waves from colliding black holes. We have landed robots on Mars. Yet, if you open any undergraduate textbook, 50% of the pages are just analyzing this toy. It feels like a scam. It feels like physicists are lazy. They even joke that if you ask a physicist to analyze a biological organism, like a cow, they would start with a ridiculous assumption. Assume the cow is a sphere attached to a spring. But there is something they didn't tell you in that lecture hall. We aren't doing this because we're lazy. We focus on this one specific problem because mathematically it is the only problem we actually know how to solve. The universe is a chaotic, nonlinear, terrifying place. The true differential equations that describe reality are monsters. They are often impossible to solve without a supercomputer. But hidden inside the mathematics of chaos, there is a loophole, a cheat code. Today, I'm going to show you that cheat code. I'm going to show you why atoms, light beams, and even the chemical bonds holding your DNA together are all just disguises for the same simple equation. By the end of this video, you will never look at a spring the same way again, because you'll realize it's not just a toy, it's the source code of reality. To understand the cheat code, you first have to understand the rule that governs everything in existence. Rule number 1. The universe is lazy. It hates potential energy. It wants to get rid of it as fast as possible. This is why water flows downhill. This is why a stretched rubber band snaps back. In the language of physics, systems always try to find the ground state, the point of lowest energy. Think about it. We don't see the unstable things. If an atom is unstable, it decays. If a bridge is unstable, it collapses. The only things that stick around long enough for us to study them are the things that have found their valley. They're trapped in a state of stability. So, if you want to understand the building blocks of reality, we don't need to analyze the chaos of the peaks. We just need to understand the geometry of the valley floor. But there is a problem. In the real world, the curve isn't simple. It's usually some nightmare function derived from quantum chromodynamics or general relativity. It's messy. So, how do we solve it? We use the translator. This is the Taylor series. If you're a student, you might remember this as a tedious homework problem, but physically, it is something much more powerful. It is an approximation machine. It says that any smooth, complicated curve can be broken down into an infinite list of simple terms added together. It allows us to translate the language of impossible nature into the language of solvable math. And when we apply this machine to our stable valley, something magical happens. The terms start to delete themselves. Let's watch the math disappear. Let's look at the first term, the constant. This number just tells us how high the valley is. Is the bottom of the bowl at 0 meters or 1,000 meters? Here's the thing about physics. Nature doesn't care about absolute altitude. Nature only cares about the change in energy. So, We can set this 0 wherever we want. It is useless. We delete it. Next up, the linear term. This represents the slope of the curve. Remember where we are? We are at the bottom of a valley. We are in equilibrium. If you place a ball at the very bottom, does it roll left? No. Does it roll right? No. The ground is flat. The slope is 0. Because we are stable, this term vanishes mathematically. And now, we are left with the survivor, the quadratic term. This is the first term that isn't 0. It represents the curvature, how steep the walls of the valley are. If we ignore the tiny high-order terms for a moment, look at what we have left. Does that look familiar? It's a parabola. And if you remember high school calculus, you know that force is just a negative derivative of potential energy. So, if we take the derivative of this parabola, the 2 comes down, the fractions cancel, and we get Hooke's law, the equation for a mass on a spring. This is the punchline. We didn't assume the universe was made of springs. We didn't simplify the problem because we were lazy. We proved that any stable system in the universe, no matter how complex, reduces to a mass on a spring, as long as you don't push it too hard. Bond between 2 hydrogen atoms? It's a spring. A bridge vibrating in the wind? It's a spring. A photon moving through an electromagnetic field? It's a spring. The Taylor series is a reason physics works. It allows us to look at the terrifying complexity of reality, squint our eyes and say, it's basically a parabola. But there is a catch. So, if the math proves that stability is just a spring, what does that imply about the universe? It implies that everything is vibration. When you look at empty space, you might see nothing. But in quantum field theory, we don't see emptiness, we see a mattress. Imagine space is filled with an infinite grid of coupled springs. If you strike this mattress, the energy ripples outward. We have a name for that ripple. We call it a particle. An electron is not a tiny red ball spinning in circles. An electron is just harmonic oscillation in the electron field. A photon is just a vibration in the electromagnetic field. You, me, the screen you are watching this on, we are just a collection of coupled harmonic oscillators dancing on the fabric of space-time. Mathematically, existence is just music. But remember that cheat code? We ignored the other terms. We deleted C3, C4, and C5. We assumed the ball stays at the bottom of the valley. But what happens if you push it too hard? If you add enough energy to a system, the approximation breaks. The linear world of Hooke's law fails. We call this anharmonicity. This is where the cubic terms come back from the dead to haunt us. This is where bridges collapse because they vibrate too much. This is where chemical bonds snap because the heat is too high. This is where the universe stops being a simple spring and becomes a chaotic monster again. The spring is a useful lie. It works perfectly until it doesn't. So, let's go back to that lecture hall. When you see that mass on a spring, it's easy to roll your eyes. It looks like a toy. It looks like a simplification for children. But now you know the truth. The drawing isn't a simplification. It's a victory. We study the harmonic oscillator not because we are lazy, and not because we are afraid of the complex universe. We study it because the Taylor series guarantees that stability looks simple. If a system exists, if it endures, if it survives the chaos of the universe without tearing itself apart, it is because, deep down, it has found a valley. It has found a way to be a harmonic oscillator. Physics is the study of how things change. But the harmonic oscillator is the study of how things stay. It is the mathematical fingerprint of existence. So, the next time your professor draws that boring little squiggle on the board, don't look at it as a metal coil. Look at it for what it really is. The only equation we actually know.